Hey everyone, welcome back. Today we are talking about DeepSeek-V4, the latest flagship open-source AI model from the DeepSeek team in China, and it is making waves across the entire AI industry. This is a full ground-up redesign, a massive 1.6 trillion parameter model that was released as an open-source preview in late April 2026. We are going to break down exactly what makes it different, why its architecture matters, how it performs against the best closed models in the world, and what it would actually take to run it yourself. Let's get into it. Let me start with the headline numbers, because they are genuinely staggering. DeepSeek-V4 Pro has 1.6 trillion total parameters. It supports a context window of 1 million tokens. That is roughly the equivalent of 10 full-length novels, all fed into a single prompt at once. And it is fully open source. The smaller sibling, DeepSeek-V4 Flash, has 284 billion parameters and also supports 1 million tokens. Both models come with 3 reasoning modes you can dial up or down. Non-think for fast responses, Think High for careful reasoning, and Think Max for maximum effort on the hardest problems. So let's start by understanding what DeepSeek-V4 actually is and where it fits. The series comes in 2 flavors. The flagship is DeepSeek-V4 Pro with 1.6 trillion total parameters. But here is the key. When processing any single token, only 49 billion of those parameters are actually activated. The lighter version, DeepSeek-V4 Flash, activates 13 billion parameters per token from its 284 billion total. This is the magic of the mixture of experts architecture. You get an enormous knowledge base, but the active computation stays manageable. You can see the benchmark comparison here. On the left, DeepSeek-V4 Pro Max goes head-to-head with Claude Opus 4.6, GPT 5.4, and Gemini 3.1 Pro across knowledge, coding, and agentic benchmarks. On the right, the efficiency chart tells the real story. As context length grows toward 1 million tokens, DeepSeek-V4 requires dramatically less computation and memory than its predecessor, DeepSeek-V3.2. More on those numbers in a moment. The series was pre-trained on over 32 trillion tokens. V4 Flash on 32 trillion, V4 Pro on 33 trillion, making these among the most thoroughly trained open-source models ever released. Here is the efficiency improvement that makes million-token contexts actually practical. In a 1 million token context scenario, DeepSeek-V4 Pro uses only 27% of the computational work, measured in flops, that DeepSeek-V3.2 required for the same task. The KV cache, which is the memory used to store the attention history, is just 10% of what version 3.2 needed. DeepSeek-V4 Flash pushes this even further. At 1 million tokens, Flash needs only 10% of the flops and 7% of the KV cache compared to version 3.2. This is not a minor optimization. This is a fundamental redesign of how attention works. Now let's go under the hood. There are 3 major architectural innovations powering DeepSeek-V4. First is a completely new hybrid attention system that replaces traditional full attention with 2 complementary compressed mechanisms. Second is something called Manifold-Constrained Hyper-Connections, which stabilizes training at trillion parameter scale. And third is a switch to a new optimizer called Muon, which replaces the AtomW optimizer that nearly all modern models have used. Each of these is a significant departure from standard practice, so let's take them one by one. This diagram shows the overall architecture of DeepSeek-V4. At its core, it is still a transformer, but with 2 new attention mechanisms: CSA, compressed sparse attention, and HCA, heavily compressed attention. These 2 are used in an interleaved pattern through all the model layers. On top of that, the standard residual connections have been upgraded to MHC, which stabilizes how signals flow between layers. For the feed-forward network layers, the model uses DeepSeek MoE, the mixture of experts system, with 384 fine-grained expert networks and 6 activated per token. Multi-token prediction is also inherited from DeepSeek-V3 to improve training efficiency. Let's look at CSA more closely. In standard attention, every token has to look back at every other token in the context. That creates quadratic cost in both compute and memory. CSA solves this by first compressing every group of M tokens into a single compressed KV entry, shrinking the total memory by a factor of M. Then, instead of attending to everything, each token uses a fast indexer, called the lightning indexer, to select only the top K most relevant compressed entries through sparse selection. There is also a small sliding window of recent uncompressed tokens to preserve local fine-grained detail. The result is much lower memory usage with very small accuracy loss. HCA, heavily compressed attention, takes the compression idea even further. Where CSA compresses tokens in groups of M, HCA compresses groups of M prime, and M prime is far larger than M. So HCA handles the long-range distant past, while CSA handles medium-range context. Together they form a complementary system across the model layers. Some layers use CSA, some use HCA, and both include a sliding window branch for local dependencies. This hybrid design is the core reason why DeepSeek-V4 can support 1 million tokens, without the memory footprint collapsing under its own weight. Two more innovations that are less visible but equally important. First, MHC, short for Manifold-Constrained Hyper-Connections. Standard residual connections in very deep networks can cause signals to explode or vanish as they travel through hundreds of layers. MHC solves this by constraining the connection weight matrices to a mathematical structure called a doubly stochastic matrix, the Birkhoff polytope, which guarantees that the spectral norm stays at most 1, keeping signals stable throughout the entire network depth. Second, the Muon optimizer. Almost every modern LLM trains with Atom W, but DeepSeek-V4 replaced it with Muon, which applies Newton-Schultz orthogonalization to each matrix update. The result is roughly twice the sample efficiency of Atom W. The model learns more per token of training data, and it also uses only 1 momentum buffer instead of 2, cutting optimizer memory overhead by half. Now let's look at the results. DeepSeek-V4 Pro Max has been tested against GPT 5.4, Gemini 3.1 Pro, and Claude Opus 4.6, the best proprietary models available right now. These are models that cost hundreds of millions of dollars to develop and run. DeepSeek-V4 Pro is open source, downloadable, and fine-tunable, and it is competing directly on the same leaderboards. That by itself is a remarkable statement about where open-source AI now stands. Here is the detailed comparison table. On MMLU Pro, which tests broad academic knowledge, DeepSeek-V4 Pro Max scores 87.5, exactly tied with GPT 5.4. On GPQA Diamond, testing PhD-level scientific reasoning, it hits 90.1. On Live Codebench, which measures real coding ability on recent problems, it scores 93.5, higher than both GPT 5.4 and Gemini 3.1 Pro. On Codeforces, the international competitive programming platform, it reaches a rating of 3206, the highest of any model in this comparison. And on SWE Verified, which tests real GitHub issue resolution, it achieves 80.6%. This table shows how V4 Flash and V4 Pro compare across their 3 reasoning modes. In non-think mode, both models are roughly competitive on many tasks, but when you turn on Think Max, the Pro model separates significantly. Flash Max still reaches a Codeforces rating of 3052 and 79% on SWE Verified. Genuinely excellent numbers. The interesting insight is that Flash, given a large enough thinking budget, can approach Pro on hard reasoning tasks. For users who need cost efficiency and speed, Flash Max is a very compelling option. On the top, you see formal mathematical reasoning results. DeepSeek-V4 achieves a perfect 120 out of 120 on Putnam 2025, the highest level of competition math, by combining informal reasoning with formal lean verification. On the bottom is the MRCR long context retrieval task, which tests whether the model can find specific information buried in very long documents. DeepSeek-V4 Pro Max maintains strong performance all the way out to 128,000 tokens, and at 1 million tokens still achieves competitive results, actually outperforming Gemini 3.1 Pro on MRCR while remaining close behind Claude Opus 4.6. For real-world coding, DeepSeek ran an internal evaluation with 50 engineers and around 200 challenging tasks spanning PyTorch, CUDA, Rust, and C++. DeepSeek-V4 Pro Max achieved a pass rate of 67%, well ahead of Claude Sonnet 4.5 at 47%, and close to Claude Opus 4.5 at 70%. In a follow-up survey of 85 DeepSeek developers, 52% said they would adopt V4 Pro as their primary coding AI, with 39% leaning toward yes. That kind of real-world validation from engineers who work with this model every day is more meaningful than any synthetic benchmark. Now the big question. Can you actually run this thing yourself? Yes, in principle. It is open source and the weights are available, but 1.6 trillion parameters is genuinely challenging to host. Let's look at what the hardware requirements actually are, and then what strategies exist to make local deployment practical for different budgets and use cases. Here is the honest picture on VRAM. At BF16 full precision, all 1.6 trillion parameters require about 3.2 terabytes of GPU memory. That means dozens of high-end data center GPUs. At FP8, you need about 1.6 terabytes. At 4-bit quantization, about 800 gigabytes. DeepSeek ships the official weights in mixed FP4 and FP8 precision. The large expert network parameters use 4-bit FP4, while the sensitive attention and routing components stay at 8-bit FP8. This mixed approach minimizes quality loss while keeping the storage footprint as low as possible. The key to making local deployment work is the 49 billion active parameter footprint. At FP8, the active compute pathway requires only about 49 gigabytes of VRAM that fits on a small cluster of high-end consumer or professional GPUs. The remaining inactive experts can live in system RAM or NVMe storage and be swapped in on demand. Community experiments show that up to 95% of certain weight layers can be offloaded from VRAM entirely. NVIDIA's upcoming DGX station, with its 775 gigabytes of coherent memory, is designed almost perfectly for this workload, potentially enabling V4 Pro to run on a single desktop workstation. The bigger story here goes well beyond the benchmark numbers. DeepSeek-V4 signals a genuine shift in the economics and geopolitics of frontier AI. For the first time, a fully open-source model is competing directly at the frontier tier. DeepSeek has achieved deep hardware compatibility with Huawei Ascend chips, reducing dependency on NVIDIA CUDA. Expected API pricing is 20 to 50 times cheaper than equivalent Western models. And the architectural innovations, sparse attention, Muon training, expert offloading, prove that you do not need unlimited GPU clusters to reach frontier intelligence. Efficiency, not scale alone, is the new frontier. That's it for today. See you in the next one.